Application example. In order to aid us in understanding the programming and application of the SR489 relay, we will use the following application example. For our example, we will be protecting a 322 MVA synchronous generator with a voltage rating of 18 kilovolts. We will run at a power factor of 0.9 on a 60 Hz ABC rotation system. Through fault analysis studies, we have determined that the maximum fault current that we can expect to see will be 44,525 amps. There is also some additional information provided for our generator that will be used specifically for negative sequence and loss of excitation protection. This information is as follows. Synchronous reactance of the generator is 1.939 per unit. Transient reactance of the generator is 0.325 per unit. Subtransient reactance of the generator is 0.232 per unit. And finally, the I²T capability of the generator is 10 and I² continuous capability is 8%. These values will be discussed in more detail under the specific protection elements that they pertain to. We must first calculate the nominal current of the generator, allowing us to select appropriate CTs for our system. The I nominal is equal to the generator power rating divided by √3 times the nominal voltage. We know that the power rating of the generator is 322 MVA, and the nominal line-to-line voltage is 18 kilovolts. By entering these values into our formula, we determine that the nominal current of our generator is 10,328.15 amps. When selecting the CTs for our generator, we want to make sure that the nominal current falls between 50 and 100% of the CT primary. The closer the nominal current matches the CT primary, the more accurate the current metering will be. As we cannot match the calculated nominal currents exactly to an available CT primary, we will use 12,000 to 5 CTs. This wiring diagram will provide the additional information required for the relay's configuration. As mentioned earlier, the CTs will be selected as 12,000 to 5 CTs. We will be using the same CT ratios for both the output and the neutral CT connections. It is important that when these CTs are purchased, match set or identical CTs should be used on both the neutral and output sides of the generator. Y-connected PTs will be used with a ratio of 18,000 to 120 volts. We will also be using a neutral VT connected directly to the neutral leg of the transformer with a ratio of 14,400 to 240 volts. For our ground current protection, a zero-sequence 50 to 0.025 amp CT will be connected to the neutral end of the transformer. The R1 trip contact will be connected to the trip coil of our breaker, with the trip coil supervision wired in parallel to this circuit. The R5 alarm relay will provide alarm element information to our PLC. The 52A contact from our breaker will also be wired into the breaker status input of the relay. We are now ready to program the SR489 relay as per our system specifications and requirements. This section will provide an example of programming a relay using the EnerVista 489 setup program. The first step in using the setup program is to configure the communications to allow us to talk to the relay. We will do this by selecting the Device Setup button located above the online window on the left side of the screen. In the window that appears, you will see the panel on the left-hand side showing the text, "Please add a site." This indicates that no sites or devices have been set up for communications. First, we need to add the site that will contain the relay. Press the Add Site button found at the top of the window. A new site will be added with the default name, New Site 1. To change the name of the site, click on the Site Name field and type in a new name. Next, we will add all of the devices that we want to be found in that site. Highlight our site by clicking on it and press the Add Device button, and a new device will be added to the site with a default name, New Device 1. We now need to configure that newly created device. In the panel on the right, click on the Device Name field. Type in a new name that describes that relay. Open the pull-down menu. Because we are configuring to communicate with an RS-232 serial cable, we will select Serial from the menu. Several new fields will appear in the area below. The Modbus slave address is used to identify specific devices for communicating on the network. When communicating through the front port, there is only one device on the network. Therefore, there is no risk of communicating with the wrong device. For this reason, we can leave the Modbus slave address to the default of 1. In the COM port field, select the communication port of your computer that the serial cable is connected to. The COM port that we are using is COM1. Therefore, we will leave this at the default. The baud rate has been set to 9600. The order code and firmware can be read from the relay itself to fill in the last two fields. Press the Read Order Code button. Press the OK button. Basic Setup. The following section will provide simple instructions for using the EnerVista 489 setup program to configure the SR489 relay. Once the device setup has been completed, you will see the name of the site you have created in the device window. By opening this menu, you will see the name of the device that was set up for communications. Opening this menu further, you will see the menu structure for the relay itself. This is one of two methods that can be used to view the settings and actual values that are present in the relay. By selecting the settings and then the SR489 setup, you will see the available settings for the basic operations of the relay. By double-clicking on a settings menu, you will see the specific settings for that function. For example, by double-clicking on passcode, you will be able to see the settings for enabling and disabling the passcode protection. The second method for viewing the settings in the relay is to click on the Setpoints drop-down menu located at the top of the EnerVista 489 setup window. This will show a list of all settings pages within the relay. Please note that the grouping under the Setpoint drop-down menu matches the structure of the setpoint pages found in the relay. If you familiarize yourself with the menu structure by using the PC program or the keypad, the transition to the other interface will be very simple. Select SR489 Setup. A window will open that displays all submenus, including passcode. Clicking on the Passcode tab allows you to view the settings for enabling and disabling the software security. Customizing the appearance of the setup program can make it easier to navigate the settings of the relay. For instance, the settings windows can be resized. For this training CD, we will be using the drop-down menus located at the top of the window, so we can close or shrink the file and device windows to allow a larger viewing area for the settings. Double-clicking on the border of the settings window will size it to the available viewing area. We will now program the basic relay setpoints required to protect a generator. The values we will be using are intended only as an example. Let's start by entering some of the basic settings required for the 489 relay to operate properly. The first is the passcode. This setting, in combination with the hardware setpoint access switch mentioned earlier, provides security for the relay and its settings. Setpoint access will let you know if the relay allows setpoints to be written to the device. If the access states read-only, then the device has been passcode protected. All relays are defaulted from the factory with no passcode protection. To enable the passcode protection, click on the Change Passcode button and enter your passcode twice. You can now select the Restrict Access button. If you forget your passcode, there is an encrypted passcode provided. Please record this encrypted passcode and call GE Multilin Technical Support for assistance. If you wish to disable the passcode protection, simply change the passcode to 0. This will remove any passcode protection from the relay. To ensure that the recorded events and waveform files are time and date stamped correctly, select the Real-Time Clock tab to set the date and time. You can choose to synchronize the relay date and time to your computer using the Sync Relay to Computer button, or you can store the date and time manually by entering the information and selecting the Set Manual Date and Time button. If more accurate time stamping is important to your application, it is possible to connect the SR489 to an iRig-B generator. You must select the iRig-B type as either DC shift or amplitude modulation. When you have changed a setting in the PC program, the new setting does not take effect until it has been saved to the relay. Always click on the Save button after making the necessary changes to the settings. The SR489 relay will learn and remember various calculated and metered values from the system. This information is very useful when reviewing system performance, as well as planning preventative maintenance. It is very important that this information is cleared inside the relay after relay testing or when installing the relay on a new generator. Select the Clear Data tab in order to reset this information. You will see a number of variables, each with its own Clear button. As we are installing this relay on a new generator, select each of the Clear buttons individually. After each clear is performed, you will see a message indicating that the command was completed successfully. System Setup. This section will illustrate how to program the relay to properly detect current and voltage levels, as well as program the parameters of the generator that we will be protecting. In order to properly meter and provide protection, the relay must know the specifics of the system it is connected to and how it is connected to the system. The first step is to program the current transformers that we will be using. Select System Setup and Current Sensing from the Setpoint drop-down menu. The first setting that is available to us is the Phase CT Primary. In order to enter this parameter, select the current setting of Off. You will see 3 arrows appear on the right-hand side of the setting field. The smaller up and down arrows can be used to increment the setting by 1 amp, while the larger arrow will open up an interface that will allow you to program the value using a keypad similar to a calculator. Select the large arrow. During the application example section of this CD, we determined that the CTs we would be using would have a ratio of 12,000 to 5, so we will enter 12,000 as the CT primary. When the value is entered, click on the Accept button. Next, we will need to enter the type of ground CT we will be using. Click on the right-hand side of the ground CT parameter to view all available options. We can choose either a 5 amp or 1 amp secondary, or the 50 to 0.025 amp CT. For our example, we will select the 50 to 0.025 amp CT. Select the Save button to store these settings to the relay. We will now program the settings for our voltage transformer connections. Select the Voltage Sensing tab. Clicking on the VT Connection Type parameter will allow us to view all available options. We can choose to either have a Y or open delta connection, or none if we have chosen not to install VTs in our system. We will select the Y connection as per our system specifications. We will now be able to view additional settings for the voltage configuration. The transformer ratio must be programmed as a value to 1 ratio, so we will need to convert our 18,000 to 120 to an acceptable setting. In order to do this, we simply divide 18,000 by 120, giving us a value of 150. This will be programmed by again selecting the right-hand side of the transformer ratio field. As we will be using a neutral voltage transformer, we must change the neutral voltage transformer parameter to Yes, allowing us to program the ratio. The ratio must again be programmed as a value to 1 ratio. Our 14,400 to 240 ratio will convert to 60 to 1. Finally, we must program the generator parameters. You will notice on the front of your relay that the in-service LED is not illuminated. As a precautionary measure, the relay will not provide any protection until the generator settings have been entered. This will prevent relays from being placed into service without all of the necessary information being programmed. Select the Gen Parameters tab to complete the system configuration. The first setting which must be entered is the rated MVA of our transformer generator. For our example, this will be programmed as 322 MVA. We know from our example that the rated power factor is 0.9 and that the nominal voltage of the generator is 18 kilovolts. Finally, the nominal frequency of our system is 60 Hz with an ABC rotation. When all parameters have been programmed, select Save. You will notice that the in-service LED on the front of the relay will now turn on. The relay is ready to monitor the system voltages, currents, and power. Digital inputs. The SR relay has a total of 9 digital inputs available, 7 of which are user configurable, while 2 are predefined as the breaker status and setpoint access switches. Select Digital Inputs from the Setpoint menu to view the available options. We will first select the breaker status. This setting allows a 52A or 52B contact to be wired to the relay. This is required for proper operation of the relay, as it allows the relay to know if the breaker is open or closed. As our system is using the 52A contact, we will leave this at its default value. There are a number of predefined options available for the user programmable inputs. Select Predefined from the Digital Input menu. You will see 8 different options available, ranging from remote trips to changing setpoint groups. If your specific system requires an operation not available in the Predefined section, you can create your own operation under the General Purpose section of the Digital Inputs. Select Digital Inputs and General Purpose from the Setpoint menu. You will now see 7 tabs available, allowing all 7 user programmable inputs to be configured separately. To assign a digital input to one of these general inputs, simply change the Assign Digital Input parameter to the number of the input you wish to use. For example, change the parameter for General A to Input 1. Settings will now be available for programming the input to operate a trip, alarm, or a control. You can also program a custom name for the digital input. This name will be displayed on the display of the relay whenever the input has been asserted. As we will not be using any inputs other than the breaker status, we can close all open windows without saving the changes we have made. Output contacts. The SR489 relay offers a total of 6 output contacts, 5 of which are user programmable to operate in conjunction with the trip, alarm, and monitoring functions of the relay. The one exception is the service relay, which will only ever operate if there is an internal failure detected within the SR489. Select Output Relays from the Setpoint menu to view the available settings. The operation of each of the trip, alarm, and auxiliary relays will be programmed under the settings for the individual protection elements. The only settings that are available in this section of the programming is what type of reset can be used to reset a latched operation of the element. For example, select the R1 trip parameter. You can see that the R1 trip relay can be programmed to allow all resets or remote resets only. All resets will allow latched trips to be reset using either the reset button on the front of the relay or by using a remote reset signal assigned to one of the digital inputs. Selecting Remote Reset Only will disable the reset button on the front of the relay for resetting latched trips. For our system, we will want to allow all relays to be reset using the front panel buttons, so we will leave all settings as All Resets. Now that we've programmed the basic set points that the relay needs to monitor the system, let's take a minute to look at where the relay displays the metered and calculated values from the system. Select the Actual drop-down menu. The subheadings in this menu contain all metered values in the system, the current status of inputs and outputs, as well as historical data such as the event recorder and oscillography files. The status menu will contain the status of any active trips or alarms, as well as the generator status and the state of all contact inputs. Any metered or calculated values from the relay can be found under the Metering subheading. There are tabs available for displaying real-time currents, voltages, and RTD temperatures, as well as the calculated power and demand values. The metered analog input values will also be available here if they've been programmed. One of the strongest tools available with this relay is its event recorder. The event recorder runs constantly, recording the system and relay status whenever a trip occurs. Information such as current amplitude and angle, voltage levels, RTD temperature, and differential currents will be recorded for every event. The event recorder can store up to 128 events. If the number of events exceeds 128, the oldest events will be replaced with new events. This information is non-volatile and will not be lost if the power to the relay is removed. Let's take a closer look at how to access the event information. Select the Event Recorder from the Actual drop-down menu. At the top of the event window, you will see a list of all events that have occurred in the relay. This list will include the time, date, and cause of the event. If you scroll down, you will see a drop-down bar for selecting the specific event number you wish to look at. We will choose event number 223, listed above as On Self-Test Relay. Scroll further down the page. Now we can see the metered information from when the event occurred. This is a snapshot of the exact values seen by the relay when the event occurred. There are 2 buttons on the right side of the screen. The Clear Events button will reset the event recorder, deleting all event data from the relay, We will select the Save Event Data button so that we can store a soft copy of the events for future analysis. You will be prompted to save either all of the events in the event record or only the events that have been selected. We will choose All. It is important when naming the event file that the extension remains as CSV. This will allow the events to be opened in Microsoft Excel. You now have a permanent copy of the events and can reset or clear the events in the relay. We will do this by simply selecting the Clear Events button. When the clear is complete, no events will be listed in the event recorder. The Waveform Capture is an invaluable troubleshooting tool provided with the relay. It will capture an oscillography file whenever a trip event is recorded by the relay. These waveforms show the current, voltage, and digital waveforms for before, during, and after the trip. The waveforms are stored in volatile memory, so any loss of control power will cause the information to be lost. Waveforms should be stored prior to removing the relay from the system for maintenance. To access the Waveform Capture, select Waveform Capture from the Actual drop-down menu. In this window, you will see the total number of waveform captures that are currently stored in the relay, as well as a drop-down tab for selecting which waveform you wish to view. There are also buttons available to manually trigger a waveform and to save the waveform to a file. As we currently don't have any waveforms present in our relay, we will select the Trigger Waveform button. You will see the total triggers increase to 1. To the right of the Trigger Waveform button, you will see a button for launching the viewer. Click this button to view the selected waveform. When the viewer opens, you will see the waveforms displayed in the bottom right-hand window. This window operates very much like an oscilloscope. There are 2 cursors, colored blue and green, which can be moved horizontally along the waveforms. The window to the left of the waveform will display the metered values at the position of the cursors. You can select to view either or both of the cursors, as well as the delta value between them by selecting any combination of the 3 buttons at the top of this window. The red line in the waveform window indicates the moment when the waveform was triggered. As per our settings discussed under the Basic Setup section of this CD, 75% of the waveform will be viewed as pre-trip data, while 25% will show post-trip data. To save this waveform to a file, simply close the viewer window and select the Save to File window. You will be prompted to enter a name and location for the file. Select Save to finish. Product information will provide hardware and software information specific to this relay. This information includes serial number, firmware or software revision, and the order code of the relay. The original factory calibration date, as well as the last date of calibration, is also available here. The trending is similar to the waveform capture, providing historical system information. The difference is that the trending file can be programmed to capture only the analog values that are required. Data will be captured at time intervals determined by user programmable set points. The front panel will open up an HMI display, allowing a visual representation of the front of the relay to be displayed within the PC program. This is useful when communicating to a relay that is not near your computer. Phase overcurrent. We will now set up the basic protection elements required to protect a generator using the SR489 relay. The first elements that we will program are the phase and high set phase overcurrents. Select the Settings drop-down menu, Protection, and Current elements. All phase, ground, and negative sequence overcurrent elements will now be available. Select the Phase Overcurrent tab to access the settings. The phase overcurrent element is designed as a timed overcurrent element, or TOC. It is used for coordination with other protection devices in the system, and will use an inverse curve to determine the tripping time of the element based on the magnitude of the fault current. The first setting seen is the function. This will determine what operations the relay will perform if the TOC element operates. Setting this function to off will disable the TOC element. A setting of latched will operate and latch the trip output contact when the phase current levels exceed the programmed set point for the designated amount of time. A manual or remote reset will be required to reset the trip contact. A setting of unlatched will operate the trip output contact when a fault occurs, but will reset the output contact when the condition causing the fault is removed. We will program this element as latched, as we wish the trip contact to remain asserted until manually reset. The phase overcurrent trip relays parameter allows the user to program which of the output contacts will operate when an overcurrent trip is issued. This is generally set to relay 1, as that is the trip contact for the relay, but a combination of trip and auxiliary relays is programmable by selecting the parameter. For our application, we will use only relay 1, the trip relay. The Enable Voltage Restraint parameter allows the relay to automatically adjust the pickup level of the overcurrent element based on the level of voltage present in the system. It will lower the pickup level during undervoltage conditions, allowing faster tripping due to overcurrent conditions. We will leave this as disabled. The pickup setting will tell the relay what level of system current will initiate the phase overcurrent protection. This setting is a multiple of the CT primary and should be set slightly higher than the nominal current rating of the generator. For our system, we will want to initiate the TOC element at 11,000 amps, 7% higher than our nominal current of 10,328 amps. As we are using a CT primary of 12,000 amps, we will need to set our pickup level to 0.92 times CT. The relay supports 14 different TOC curves, including ANSI, IAC, and IEC industry standards, as well as custom flex curves. Flex curves will be used when the predefined curves do not exactly match the system coordination requirements. For our application, we are not providing coordination with any other devices, so we will select the ANSI Extremely Inverse curve, as it provides rapid tripping times. The curve multiplier setting allows the tripping times of the relay to be adjusted without changing the shape of the curve. For example, using a multiplier of less than 1 will reduce all of the trip times equally, while a multiplier greater than 1 will increase all of the trip times equally. We will leave this defaulted to 1, using the defaulted trip times of the ANSI Extremely Inverse curve. The reset setting determines how the TOC will reset the time to trip after the overcurrent condition has been removed. A setting of linear is used when coordinating with electromechanical devices, as it provides a timed resetting of the element similar to the resetting of the electromechanical induction disk. We will select the Instantaneous Reset, which will reset the time to trip as soon as the overcurrent condition is removed. The SR489 also offers a Phase Instantaneous Overcurrent, or IOC element. This is designed to initiate a trip at current levels where damage to the generator and surrounding components requires immediate isolation without consideration for coordination. Select the High Set Phase Overcurrent tab to program the IOC element. We will again program the trip as latched and use only the R1 trip output contact. The pickup level must be set lower than the maximum expected fault current, which in our application is 44,525 amps. We will use a pickup value of 3.5 times CT, or 42,000 amps. An intentional delay can be programmed for this element intended to avoid nuisance trips due to transients. This setting will be programmed to 100 milliseconds. Select Save to store all settings to the relay. Ground Overcurrent. Select the Ground Overcurrent tab from the current elements to review the available settings. This element offers both an alarm level as well as a trip level to be programmed. We will start by programming the alarm. Change the alarm parameter to latched. Multiple combinations of output contacts are available under the alarm relay's parameter. However, we will use only output relay 5 as it is the alarm contact for the SR489 relay. As per our system specifications, this contact will be wired back to our PLC to provide indication of any alarms generated by the 489. The alarm level will be set to a value that indicates there is a fault in the system, but the fault has not yet reached a level that requires the generator to be isolated. We will leave the default pickup setting at 0.2 times CT. As we are using the 50 to 0.025 amp ground CT, this setting will mean that 10 amps of fault current in the system will cause the relay to alarm. We will also program in 3 cycles of intentional delay. That will avoid nuisance alarms from occurring due to transient conditions. The ground overcurrent alarm events setpoint will determine if the ground fault alarms are written to the event recorder. We will program this parameter to on, as we wish to have all system events recorded for fault analysis. The ground overcurrent trip settings will also be enabled as a latched element, again using only the Relay 1 trip output contact. The pickup level for this element will be programmed to 0.3 times CT, or 15 amps of ground fault current. The same predefined and custom flex curves that were available for the phase overcurrent protection are also available for the ground overcurrent element. We will again use the ANSI extremely inverse curve with a multiplier of 1 due to its rapid trip times. We will select the Instantaneous Reset, which will reset the time to trip as soon as the overcurrent condition is removed. Save all settings to the device. Negative sequence overcurrent. In a perfectly balanced system, with current amplitudes being equal and each phase exactly 120 degrees apart, all current produced is considered to be positive sequence current. In reality, all systems will have a small amount of unbalance due to CT errors, as well as loading of the generator. Unbalance in the amplitude or phase angles of the currents will create a flux field with a phase rotation opposite to the phase rotation of the system. This flux field is referred to as negative sequence current. Negative sequence current will produce heat inside of a generator due to the reverse rotation of the currents. The ability of a generator to withstand negative sequence current is given in two forms. They are the negative sequence squared T capability and the continuous negative sequence current capability. The negative sequence squared T capability will take the amount of negative sequence in the system squared and multiply it by the time that the negative sequence current has been detected. This will provide the amount of heat induced due to the current unbalance. The continuous negative sequence current capability will indicate what percentage of the full load current can be negative sequence current before damage will occur in the generator. Select the Negative Sequence tab to program this element. First, we will program the alarm set points. The alarm will be programmed as unlatched using Relay 5 as our alarm contact. The alarm pickup level will be set slightly lower than the continuous rating of the generator. As our continuous rating is 8% of FLA, we will use a setting of 6% FLA. An acceptable delay for the alarm is 10 seconds, allowing for sensitive operation of the negative sequence current element while avoiding nuisance tripping due to transient faults. The negative sequence alarm events will be programmed as on, as we want any alarms recorded in the event recorder. We will now program the negative sequence trip element. The negative sequence trip will be programmed as a latched trip, operating only the R1 trip contact. Our pickup level will be programmed to the negative sequence continuous capability of our generator, or 8% FLA. The constant K is usually programmed to 90% of the I² T capability of the generator, ensuring that the element will operate before the maximum limit of the generator is reached. We will use a setting of 9. If the generator manufacturer does not specify a maximum operation time for negative sequence current, then a typical time of 3 minutes or 180 seconds can be used. This will be our overcurrent max time set point. As per IEEE standards, a linear reset time of 4 minutes or 240 seconds can be used for the reset time. Offline overcurrent. When a generator is offline, there should be no measurable current in any of the phases. The offline overcurrent protection is used to detect any generated current after the generator has been taken offline. Select the Offline Overcurrent tab. This element will be programmed as a latched element and will use the Relay 1 trip output contact. The overcurrent pickup level can be set very sensitive, as any small amount of current will indicate a fault. We will leave this programmed as 0.05 times CT. The relay will use the breaker auxiliary contacts to determine when the generator has been taken offline. As the breaker auxiliary contacts may operate faster than the main breaker contacts, we need to make sure that the programmed delay is longer than the operate time of the breaker itself. Otherwise, the element may be armed before the generator has been disconnected from the system. We will use the default 5 cycles of delay. Our relay will now monitor the neutral current CTs after the generator has been taken offline, and if current is still present in the system after 5 cycles of delay, a trip command will be issued to the breaker. Phase differential. The SR489 phase differential protection utilizes an industry-standard dual-slope % restraint characteristic. This allows a sensitive setting of the element while eliminating nuisance trips due to CT saturation caused by external faults. Select the Phase Differential tab from the current elements. The first step is to enable the differential trip as latched. As with our other elements, we will be using the Relay 1 trip output contact as the only output for this element. The minimum pickup level for the differential indicates the minimum amount of differential current that must be present in the system in order to enable the differential element. Provided that the neutral and the output CTs are identical in ratio, as well as excitation characteristics, this level can be set very low. We have purchased a matched set of CTs for our system, and they have all been tested to operate within their specified tolerances. So we will use a setting of 0.05 times CT, or 600 amps. If the metered differential current in the system is less than this value, then the differential element will be disabled. The first slope of the two-slope curve must be set high enough to compensate for the accuracy tolerances of the CTs. Our CTs were purchased with 5% tolerances. Each phase has two CTs, one on the neutral side, one on the output side. So we will have a total tolerance of 10% per phase. This will be our slope 1 setting. The second slope should be set to compensate for differential currents that will be caused by saturation of either set of CTs. During heavy through-fault conditions, it is possible that the high levels of fault current could cause one of the CTs to saturate. This saturation will cause higher levels of differential current to be seen. We do not want the 489 to trip on this differential current as the fault is external and should be isolated by other protection devices. To protect against nuisance tripping due to external faults, we will set the second slope to 80%. The delay set point allows an intentional delay to be programmed for this element. We will leave this value defaulted to 3 cycles to avoid nuisance tripping due to transient conditions. Save all settings to the relay. Inadvertent Energization. The inadvertent energization protection is designed to protect against bringing the generator online when it's at a standstill or when the speed is significantly lower than rated speed. The relay will monitor the voltage and current levels when the breaker is closed, and if current is present without the expected levels of voltage, a trip signal will be sent to open the breaker. Select the Inadvertent Energization tab to access the set points. This element will be programmed as latched using the trip relay 1. The arming signal is used to determine what condition will cause the element to become active. We will want this element enabled when the generator has been taken offline, so we will program this parameter for under voltage and offline, assuming our VTs are located on the generator side of the breaker. This means that when the breaker opens and the voltage has dropped below the under voltage pickup level, the inadvertent energization element will be armed. If the VTs are located on the system side of the breaker and will read voltage regardless of the state of the breaker, this element will need to be programmed to under voltage or offline, as the voltage level will not drop due to the opening of the breaker. The generator manufacturer will generally provide a current pickup level for this element. If it has not been provided, which is the case with our application example, a value of 20% of the rated current is acceptable. The nominal current previously calculated for our generator is 10,328.15 amps, giving us a pickup value of 2,065.5 amps or 0.17 times CT. The standard pickup level for the undervoltage pickup level is 70% of rated. Our relay is now programmed to trip the generator if the breaker is closed and current is higher than the 0.17 times CT, while the voltage level of the generator is less than 0.7 times the rated voltage. Be sure to select Save to store all settings to the relay and close all programming windows. Loss of excitation. The loss of excitation is designed to protect the generator from a severe loss in the exciter field. It is based on 2 separate Mohs circles, whose parameters are based on the secondary impedances of the generator. The 2 Mohs circles are represented as follows. Under normal operation, the generator will export both real and reactive power. When a fault occurs that results in loss of the exciter field, the generator will continue to export real power, but will begin to import reactive power, creating instability in the system. As the generator starts to import reactive power, the impedance viewed at the generator terminals will move from the top right quadrant of the graph, moving towards the 2 circles. A trip will occur when the output crosses one of the circle parameters. Select Protection, Voltage Elements, and the Loss of Excitation tab from the Setpoint drop-down menu. The first parameter seen is used to enable voltage supervision. This setpoint will allow the time delays of the element to be adjusted based on the level of voltage present in the system. We will not be using this feature, so we will leave this programmed as no. The first circle trip setting will be enabled as a latched trip using our Relay 1 trip contact. The diameter and offset of the circles are determined by the secondary impedances of the generator. We know from our application example that the reactances of the generator are as follows. Synchronous reactance of the generator is 1.939 per unit. Transient reactance of the generator is 0.325 per unit. Before we can use these values, we will need to calculate the secondary base impedance of the generator and use this value to convert the synchronous and transient impedances into secondary values. To calculate the base impedance of the generator, we will use the following formula. Base impedance is equal to the nominal kV of the generator squared divided by the rated MVA, multiplied by the CT ratio divided by the VT ratio. We know from our example that the generator rated voltage is 18 kilovolts and the rated power is 322 MVA. We are using 12,000 to 5 CTs and 18,000 to 120 volt VTs. Filling in the formula, we calculate the base impedance of the generator to be 16.099 ohms. We can now calculate the secondary synchronous and transient impedances. The secondary transient impedance is equal to the transient reactance per unit multiplied by the base impedance of the generator. Using the per unit value of 0.325 given by the manufacturer and the calculated base impedance of 16.099 ohms, we calculate that the secondary transient impedance is 5.232 ohms. The secondary synchronous impedance is equal to the synchronous reactance per unit multiplied by the base impedance of the generator. Using our known values, we calculate the secondary synchronous impedance of the generator to be 31.215 ohms. We are now ready to calculate the offset and diameter for the two Mohs circles. For circle 1, the offset is given as the secondary transient impedance of the generator divided by 2, and the diameter is equal to 0.7 times the secondary synchronous impedance. Using the calculated values for the secondary synchronous and transient impedances, we calculate the circle 1 offset to be 2.62 ohms and the diameter to be 21.85 ohms. Program the offset and diameter of the circle using a time delay of 0.1 seconds to avoid maloperation during switching transients. We now need to enable the second circle as a latched trip, again using the Relay 1 trip contact. The offset for the second circle will be programmed the same as the circle 1 offset. The diameter of the second circle will be programmed as the secondary synchronous reactance of the generator, or 31.215 ohms. A minimum time delay of 0.5 seconds is recommended to prevent maloperation during power swinging conditions. Program all set points and select Save to store the parameters to the relay. Phase voltage elements. Overvoltage conditions in a generator are usually caused by a failure of the voltage regulator or a sudden rejection of load. Generators are designed to operate continuously at a maximum of 105% of rated voltage, and any sustained operation above that level can cause permanent damage to the generator's insulation. Select the Overvoltage tab to program the parameters for this element. The overvoltage element is primarily used for alarming and not for initiating a trip of the generator. We will program only the alarm using the unlatched set point. The alarm output relay 5 will again be the only contact used. The alarm pickup will be set slightly higher than the acceptable 105% of rated load. We will use a setting of 110%. A delay of 10 seconds will be programmed to allow time for the automatic voltage regulator to compensate for any loss of load conditions. The overvoltage alarm events will be programmed to on, making sure that any overvoltage conditions will be documented in the event recorder. Undervoltage conditions within the generator can be as detrimental to the system as overvoltage conditions. Operating a generator with terminal voltages less than 95% of its rated voltage can result in instability of the power system, import of excessive reactive power from the grid, as well as failures in voltage-sensitive devices and equipment. The undervoltage element of the SR489 is only active when the generator is online and when the phase currents are metered above 7.5% of the CT primary. Select the Undervoltage tab to access the settings. Undervoltage protection is usually programmed in two stages using both the alarm and trip elements. We will program the alarm as an unlatched element using output relay 5. The alarm will be set to operate at 0.9 times the rated voltage with a delay of 10 seconds. The delay is programmed to avoid nuisance operation of the element during transient faults. The alarm events will be programmed to on. The trip element will be programmed as a latched element, set to operate at 0.8 times the rated voltage. We will program a shorter time delay than the alarm using a setting of 2 seconds. The undervoltage curve reset rate will determine how long the undervoltage element takes to reset after the undervoltage condition has been removed. We will program a reset rate of 1.4 seconds. The final setting allows us to program the undervoltage trip to operate as a definite time element or as a curve, where the trip time will be determined by the magnitude of the undervoltage condition. We want our relay to trip at 2 seconds when the terminal voltage drops below 80% rated voltage, regardless of how far the voltage drops, so we will use the definite time parameter. Select Save to store all settings to the relay. Neutral voltage protection. The neutral overvoltage or fundamental frequency and neutral third harmonic undervoltage elements are used to provide 100% stator ground fault protection of the stator winding. First, we will program the neutral overvoltage element. Select the Neutral Overvoltage Fundamental tab. We will be using only the trip function for this element, and it will be programmed as latched. The trip relay 1 will be our only output contact. The neutral overvoltage protection responds to the fundamental frequency and is typically set to 95% of the generator stator windings voltage. We must first calculate the maximum neutral voltage possible in our system. It is necessary to represent this value as the secondary voltage of the neutral grounding transformer. To do that, we will use the following formula. V neutral secondary is equal to the nominal voltage of the generator divided by √3 times the neutral VT ratio. Using our generator voltage of 18,000 volts and a neutral VT ratio of 14,400 to 240, we calculate a neutral voltage of 173.2 volts. To calculate the pickup level, we simply take 5% of the calculated secondary voltage, or 0.05 times 173.2 volts, resulting in a pickup level of 8.7 volts. The time delay for this element should be greater than the time required to clear faults outside the generator zone of protection. For our example, we will assume a maximum fault clearing time of less than 13 seconds and use a delay setting of 13.4 seconds. A standard setting of 1 second will be used for the neutral overvoltage curve reset rate. Select Save to store the settings to the relay. The neutral undervoltage will now be programmed to allow 100% stator ground protection. Select the Neutral Undervoltage Third tab. We will again be using only the trip function of this element, programmed as latched, using only the trip output relay 1. Before we program the pickup level for this element, we must determine the expected levels of third harmonic voltage present in the neutral of the generator under normal operating conditions. For our example, we will assume that under normal operating conditions, the third harmonic voltages will make up 2% of the rated voltage. To calculate the maximum amount of third harmonic voltage that could be present in the neutral leg of our generator, we will use the following formula. Third harmonics, primary value, is equal to 2% times the generator rated phase-to-phase voltage divided by the square root of 3. We will then use this calculated third harmonic value to determine the harmonic content that will be present on the secondary side of the neutral VT. We will simply divide the calculated primary value by the neutral VT ratio. Using the information from our system, our formulas will look like this. We now know that during normal operation of our generator, the third harmonic content of the neutral voltage will equal 1.38 volts. When a fault occurs, the level of third harmonic voltage is expected to drop. We will program the pickup level for this element to 1.2 volts. A typical time delay of 5 seconds can be used for this element. Frequency elements. The first frequency element that we will be programming is the volts per hertz element. This element is designed to protect against overexcitation of the generator. We will only be programming the tripping function of this element. Enable the trip as latched using the Relay 1 trip output contact. A typical pickup level for this element is 1.18 times nominal, with a delay of 5 seconds to avoid nuisance tripping. We will leave the reset rate of the element at 1.4 seconds and use the default set point of definite time. Select the Under Frequency tab. In order to prevent nuisance tripping of this element, we will block the under frequency from online for 1 second. This will prevent trips if the generator is being synchronized to the system. We will program the voltage level cutoff to 0.5 times the rated voltage to make sure that this element is only armed when the breaker is closed and voltage is being metered. Enable the trip as latched using the Relay 1 trip contact. You will see that there are 2 separate trip levels and delays that can be programmed. This allows for more serious faults to initiate a trip faster than less aggressive faults. Standard settings for the tripping of this element are as follows. Trip level 1 will be programmed to 59.5 Hz with a time delay of 60 seconds. Trip level 2 will be programmed to 59.0 Hz with a time delay of 30 seconds. Program all parameters and save settings to the relay. Select the Overfrequency tab. We will again program this element to be blocked from online for 1 second with a voltage level cutoff of 0.5 times the generator rated voltage. This element is programmed similar to the under frequency protection using 2 separate stages and time delays. The settings will be as follows. Trip level 1 will be programmed to 60.5 Hz with a time delay of 60 seconds, and trip level 2 will be programmed to 61.0 Hz with a time delay of 30 seconds. Save the settings to the relay Low forward power. To program the low forward power element, select Protection and Power Elements from the Setpoint drop-down menu. Click on the Low Forward Power Alarm tab. This element is only active when the generator is online and will be blocked for a programmable amount of time once the generator is detected to be online. The blocked low forward power from online setpoint should be programmed to slightly longer than the normal loading time of the generator under normal operating conditions. For our application, we will use a setpoint of 30 seconds. We will first enable the alarm as latched using the Alarm 5 output contact. We will use the default pickup level of 0.05 times the rated megawatt, as this is standard in the industry. A delay between 20 and 30 seconds is typical for this element, so we will program the delay as 30 seconds. The alarm events will be enabled. Select the Low Forward Power Trip tab to program the tripping parameters. The trip will again be blocked from online for 30 seconds. The trip will be enabled as latched using the Relay 1 trip contact. The typical setting for the trip pickup is 0.02 times the rated megawatt with the standard 30 seconds delay. Program these parameters and select Save. Close all windows. VT fuse failure. There are a number of elements within the SR489 relay that are designed to monitor the generator and surrounding equipment for failures other than electrical faults. These elements are found under the Monitoring section of the Setpoints menu. The first monitoring element that we will program will be the VT fuse failure protection. The 489 relay will detect a fuse failure when there are significant levels of negative sequence voltage present without the corresponding levels of negative sequence current, or if the generator is online without appropriate levels of positive sequence voltage. There are no programmable pickup levels for this element. We simply need to enable the alarm as latched and make sure that our Alarm Relay 5 is being used as the output contact. We will also enable the alarm events so that we will have a record if this element operates. Breaker failure. The breaker failure protection will monitor the current levels in the system after a trip has been issued by the SR489 relay. If current levels are above the pickup level after the trip command has been issued, the element will operate. Select the Breaker Failure tab. We will program this element as a latched alarm, again using the Alarm Relay 5. As there should be no current present in the system after the breaker opens, the pickup level for this element can be set relatively low. We will use a pickup of 0.05 times CT or 600 amps. The breaker failure delay must be set longer than the expected operate time of the breaker. We will assume a 5-cycle breaker and program the delay as 100 milliseconds. Alarm events will be enabled. Our relay is now programmed to issue an alarm if the measured current in the system remains above 600 amps 100 milliseconds after the trip command has been issued. Trip coil monitor. When wired in parallel with the trip contact, the coil monitor alarm will monitor small amounts of trickle current flowing through the coil when the breaker is closed. The relay will interpret a loss of this trickle current to be a failure in the continuity of the coil. Select the Trip Coil Monitor tab. This alarm will be programmed as latched using the Alarm Relay 5. If resistors are placed around the auxiliary 52 contacts of the breaker, then this element can be enabled to operate when the breaker is open or closed. As we have not installed the resistors in our application example, we must program the alarm to only be armed when the breaker is closed, so the supervision set point will remain as 52 closed. Alarm events will be enabled to provide a historical record of any trip coil alarm operations. Maintenance. The SR489 also provides a number of monitoring elements designed to assist in planned maintenance. These are the trip counter and generator running hours elements. Select the Trip Counter tab. This element will provide an alarm when the number of breaker operations reaches a programmable level. The number of operations is based on the breaker auxiliary contact inputs to the relay to assure that even operations of the breaker not initiated by the SR489 relay are counted. We will program this as a latched alarm. The number of trips required to operate this alarm should be set to slightly lower than the number of trips required before preventative maintenance is performed on the breaker. We will assume for the purposes of our example that we wish to perform breaker maintenance every 500 operations. So we will program this element to alarm after 450 trips. The alarm events will be enabled. Select the Generator Running Hours tab. This element will alarm when the generator has reached a programmable number of hours of operation. If we were installing this relay on an existing generator, we would be able to preset the hours that the generator has already been in service. As we are designing set points for a new system, we will leave this parameter at 0. Enable the generator running hour alarm as latched using the Alarm 5 output contact. Our generator manufacturer has indicated that maintenance should be performed on the generator every 1500 hours of operation, so we will program this parameter as 1400 hours. This will allow a shutdown for preventative maintenance to be scheduled. Select Save to store all settings to the relay. Settings files. Settings files are a convenient way to store and edit offline settings for relays. Files can either be created using the EnerVista setup program, or settings already existing in a relay can be downloaded into a file. These settings can then be edited or simply uploaded back into a relay. To create a new settings file, select New Settings File from the File drop-down menu located at the top of the screen. This will open a window that will ask you to select a name for the file, as well as a location to store it. You will also be asked to set the version of the file. Select the button containing 3 dots to choose the name and location of the file. Enter a file name of default and save the file. The version of the file must now be entered before the settings file is created. The value entered here should match the firmware revision of the relay that this file will be used for. If the software revision of the relay is unknown at the time of the file's creation, default properties can be used and then changed after the settings are complete and prior to downloading the settings to the relay. We will discuss how to change the properties shortly, so for now we can use the defaults provided. Select OK to complete the default settings file. You will now see the name of our settings file appear in the file window on the lower left side of the screen. This settings file has been created with all of the default settings a relay would have when shipped from the factory. You can edit the settings of this file by simply selecting the file name and then using the Setpoints menu at the top of the screen to select the specific settings to be changed. Programming the settings of an offline file is performed exactly the same as when communicating to a relay. As mentioned earlier, existing settings can also be saved from a relay. To do this, establish communications with the relay by selecting the relay name and then choose Read Settings from Device from the File drop-down menu. Once the setup program has read the device settings, you will be prompted to enter a file name. Enter the relay name and select Save. You will now see this settings file located in the file window below our default file. To edit the settings of this file, highlight the file name and then select the settings group you wish to edit from the Settings menu. The properties of each of these files can be viewed and edited by highlighting the name of the file and then choosing Properties from the File menu. This should be done prior to downloading any settings file to a relay, as the properties of a file must match the relay properties in order for the download to be successful. Let's download the default settings file that we created to the relay. We must first check the properties of the relay. To do this, we establish communications with the relay and then select Product Info from the Actual menu located at the top of the screen. We can see from the order code that this is a 489 P5 high A20E relay with firmware revision 3.0. We now need to compare the properties of our relay to those of the default settings file. Select the file name and then choose Properties from the File menu. We can see that the file was created for a 489 relay with firmware revision 3.0. This means that our relay and file revisions are the same and the download will be successful. If the revision of the file was something other than 3.0, then we would need to change the new file revision parameter to match the firmware revision of the relay and then select Convert. As the parameters are OK, select OK to close this screen. To send the settings file to the relay, select the file name and then choose the Write Settings to Device option under the File menu. You will be prompted to select which device you wish to download the settings to. Highlight the name of our relay and select Send. The default settings will now be downloaded to the relay. Please note that settings files should never be downloaded to the relay if it is in service. Protection elements will not be able to function while the file is being programmed. Setpoints Groups. There are two settings groups available in this relay. Some applications, changing loads, or environmental conditions may require a change in the protection settings. The different settings groups allow two sets of protection elements to be programmed without changing any of the system or relay settings. Setpoint groups can either be programmed active in the settings files, or a logic input can be used to automatically switch from one settings group to another. Select Digital Inputs and Predefined from the Setpoint menu. The Assign Digital Input parameter allows the relay to automatically change which of the setpoint groups is being used by asserting a digital input. For example, if we assign Logic Input 5 to dual setpoints, anytime the Logic Input 5 is asserted, we will switch to the Group 2 protection settings. The Active Setpoint Group setting allows you to change which of the setpoint groups is being used without asserting a logic input. This is generally left programmed as Group 1. And logic inputs are used to change the groups. The Edit Setpoint group allows you to select which setting group you wish to program. The relay will still use the active group of settings for protection, but any setpoints viewed or altered using either the front display or the setup program will be from the Edit group. This is usually set to the same group as programmed under the Active Setpoint Group parameter, but can be changed to allow programming of other groups. Change this setting to Group 2. If we now select the phase differential protection that we have already programmed, we will see that all settings have been returned to their default values. This is because the previous programming was done in Setpoint Group 1. Any changes made at this point will only affect Setpoint Group 2. Anytime the relay is using the second group of setpoints, regardless of whether it has been programmed as the active group or if a digital input has been assigned and asserted, the Alt Setpoints LED will be illuminated on the front of the relay. When programming of the second setpoint group is complete, go back to the Dual Setpoint settings found under the Predefined menu and return the Edit Setpoint group to match the active group setting. This will assure that the settings seen during any troubleshooting of the system match the settings that are being used to protect the system. Firmware upgrades. Upgrades in firmware revisions allow enhancements in protection elements and operational performance of the relay. The EnerVista setup program has been designed to allow the firmware of the relay to be upgraded without requiring the relay to be returned to the factory. The latest revisions of firmware are always available on the GE Multilin website and can be downloaded free of charge. To upgrade the relay, simply establish communications with the relay using the setup program. Select the Communications drop-down menu located beside the Actual menu at the top of the screen. Click on Update Firmware. All protection elements are lost when upgrading the firmware, so this operation should never be performed on a relay that is providing protection. Select Yes to proceed. The final prompt will be to make sure that the relay's front port has been connected to the computer for the upgrade. Confirm that the connection has been made and select OK. You must now select the location where the firmware has been stored on your computer. The firmware file should be highlighted and select Open. A window will appear indicating that the firmware is being uploaded to the device. A status bar at the bottom of this window will inform you which board is being programmed. This window will close, and the relay will reset when the firmware upload is complete. All settings within the relay will be lost when the firmware is upgraded. It is very important to save a copy of the settings file prior to upgrading the firmware. The file can then be downloaded back into the relay when the firmware upload is complete.